I'm going to continue on here in chapter 2 material. And so major topics for today, electric fields and forces. Also want to talk a little bit more about electric field line diagrams. Contrast those with electric field vector diagrams, which we talked a little bit about last time. So just some reminders, there is another homework assignment due this week. There's one due on Friday on the electric field. So it's some content from chapter 2. We'll have a little more of that in the next homework assignment as well. But this will get you started here. But our first announcement for our exam, first exam, which will be next week on Thursday. So during the first hour, so we'll talk more about that on Monday, but that should be on your calendar here. So I have in the past, in this course, given students not a whole test, but like a practice exam problem. Is that something you'd be interested in doing in class on Monday? Yeah. Okay, so again, we'll treat it sort of like a pseudo test environment, you know, closed notes, and I'll give you a problem and you can try it out and then we'll talk about it. But so we'll do that on Monday then. Also, I haven't yet posted it, but I will be posting up a reading quiz for chapter 3. We'll be getting in chapter 3 probably on Monday, latter part of Monday. So I'll have you have that, read that chapter over the weekend, do that quiz. And then finally, if you are working through some of the this book here, the Image and Radio License Manual, I am posting each week some videos associated with this book. And so there's some that are from chapter 6. I'm trying to pick the chapters out that sort of align with the course a little bit best we can. So that's up there. Again, that's optional. Okay, so I think that brings us up to date here. Any questions about anything? We get going. Questions? Okay. All right, let's. I just want to briefly talk about reviewing quiz results. So sometimes students ask me, how do I see the results of my quiz? Here's how you do. So you go to My Grades in Blackboard, and then you look in the Graded tab, and you look for the quiz. So in this particular example, here's the quiz. And you'll note here that that quiz is hyperlinked, right? So it's a blue color. And so in that, you can then click on that hyperlink, and that will take you to the View Attempts page. This is more complicated than it should be in Blackboard. But anyway, here's the various attempts. In this case, there's only one attempt, but if you had more than one attempt, it would be listed there. You'll see then the grade is highlighted, blue, right? So you click on that, right there, okay? And you click on that, that will take you to the actual quiz results. And in this case, the student got 6 out of 7 points, and this one was correct, right? But this one was wrong. It tells you what the correct answer is. Okay, so if you haven't done that before, just want to know how to do it, that's how you do it in Blackboard. Okay, so if you have any questions or problems with that, let me know. But that should be how you get access. Okay, let's recap a little bit where we were last time. We left off, we were talking about how to calculate the electric field due to a point charge, right? So if a point charge of value Q, and I'm at some distance R away from that point charge, I can calculate the electric field as this formula here shows, 1 over 4 pi epsilon naught, or K, that's your electrostatic constant here, times Q over R squared, times R hat being the radial unit vector that points from the source charge, in this case Q, to some point of interest. We're going to call that typically a test location in that space. So again, just to remind you here, if we had some charge here Q, okay, and we had some point over here P, we would have some distance here R between those 2 points, and we would have an R vector which would point like that, point like this. It's a terribly unstraight line. I'll try that better again. Like that. That would point from the source charge here to the test location. Okay. So that's what we're looking at. Also, as another reminder here again, you can see here the units of this electrostatic constants are newtons, meters, and coulombs, which means that you have to have your charge in coulombs and your distance in meters for this to work out properly. Any questions about this from last time? Just as a reminder, and also this R hat vector, you can calculate it using this formula, okay? To use the formula, you do need to know the coordinates of your source charge and your test location, okay? And once you have those things, you can go calculate the difference between them, and then put those differences into the formula, and that will calculate your R hat vector. Again, just a reminder here, it's a hat vector, which means it's a unit vector. So if you get a result that's does not look like a unit vector, right, 4i plus 7j, not a unit vector, then you know you did something wrong. Okay? So make sure you can do that. And we'll practice this today. Last thing I just want to mention here, we just briefly talked about this last time, we are going to follow sort of a four-step problem-solving strategy for most of the problems in this course. So again, the planning step, what are your model assumptions? What are your key equations or steps, your approach to the problem? Just briefly, right, it's good to have a plan whenever you do anything. You want to make a drawing, so coordinate system, drawing any key points or forces or vectors, anything like that, put that on your sketch. You're going to calculate, okay, using the principles that we talk about, equations that we know, see if you can work from the things you know to the things you want to calculate, right? And lastly, make sure you check yourself over units, 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 make sure you get units in where you need them, and make sure it's just a reasonable result, reasonable number of figures. Any questions about this from last time? We're good? Okay, again, we'll practice this. I just want to remind you the principles here. Okay, so here's our problem, and I'm going to actually hand you out a worksheet so you don't have to copy this all down. Do that here first. 6, 2, 3, 5, 6. Okay, here we go. Back. 3, 6. I think that's enough for you. Okay. Okay, did everybody get one? Still coming back? No, one short. So we'll pass this back. Okay, now everybody have one. Okay, great. All right, so here's the problem at hand. We have a small sphere with charge of negative 6.5 coulombs. It's located at 2 centimeters, 2 centimeters. And we want to measure the electric field at this location, -1, -2 centimeters. So 4 steps in the problem here so far. On this page, what are the coordinates of the source charge? What are the coordinates of the test location? What is the rate of the unit vector? And then what then is the electric field at that measured location? Okay? So let's see if we can sort of break this down and go ahead and do this. All right, so here we go, 4 steps, right? Let's start off with our plan step. So what do you think we would put down here in the planning step of this problem? Thoughts? Suggestions? Yeah, in the back, what's your name?
Jason.
Jason, hey.
The information that we're given already.
Okay. Well, if it's already given to you, you don't need to write it down in the planning step. So, yeah, that's, we want something a little new here. What else could you put in the planning step? Yep.
Equation for the sphere.
Equation for the sphere. Okay, so that's one relevant equation. So let's write the equation down first. So, what's the equation again?
X squared plus y squared equals r squared, or plus z squared.
Yeah, that's equation for a circle, but not for the electric field. I want an equation for electric field.
Is it the E equation?
The equation. So what is the equation?
It's K times Q over R squared times
Okay.
R hat.
Right. So these are things, something you need to remember here. So K, so we're going to say use KQ over R squared times R hat. That's going to be our key equation to calculate the electric field. What do we need, though, to be able to use this equation? What does this assume? Remember?
Either point charges?
Point charges. Point charges. So let's go back. Does it say anything about point charges here? It doesn't say point charges. What does it say? This is a small sphere. Small sphere is not a point charge. Okay? So how do we solve the problem? Well, we're going to make a simplifying assumption. okay? We're gonna assume that if the sphere is small enough, it's going to act very much like a point charge, okay? Sort of built into that also is that we're far enough away from that small sphere so that it looks point-like, okay? And again, whenever you have to be reasonable at these assumptions, right? So, and in often cases, you'll want to go back at the end of your problem and say, does this still hold up? But for now, let's go ahead and just, we'll say we're going to model the small sphere as a point charge. Okay? And if we model it as a point charge, then yes, indeed, we can use that formula. Okay? It's always to make sure that you're writing down what you're assuming in these problems. Okay, so that's a good reasonable plan, I think, to start with. All right, next up we want to go to the sketching step. Okay? So sketching step, we want to draw in some coordinate axes. So I'm going to draw in some coordinate axes. I'm going to start with x, y here. X is this way, y that way. And what else we want to put in here? Well, we should put the location of the charge, right? That seems reasonable enough. And let's see, so I'm going to go a couple units over, a couple units up. That's going to be my charge, Q. Right, it's a negative charge. And we're also going to put in our point of interest here. That's right here. So we're going to 1 over and 2 down, and that would be some point over here. Now let's just call it point P. Not very good, P. Let's try that again. Okay, so that's a starting point. And now one other thing I want to emphasize about this sort of problem-solving strategy is that you don't necessarily have to go step, 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 right? Sometimes you're like, oh, it would be really useful to have another piece of information in my diagram. By all means, put it on there, right? I mean, this is it's you, whatever it does to help you solve the problem, right? So we may come back to this, but for now, that's, I think, a good starting point. All right, so let's continue onwards here. So let's start calculating here. I'm gonna actually start over here because I have enough space. So part A asks us what is the source charge, coordinates of the source charge in this problem. So what would you say here? What do you say? It's coordinates of the source charge here. How many charges do we have in the problem? Okay, so what are the coordinates of the source charge? 2, 2, okay? All right. So, but this is important because we're going to need this information. Right, so we're going to write down here x source, y source. I'm just going to abbreviate source with S. That's going to be 2 centimeters, 2 centimeters. Okay? Part B asks what is the coordinates of the test location? Okay, yeah. In this case, -1 centimeter. That's -2 centimeters. That's where we want to calculate the electric field. Great. Okay. Part C. Part C says calculate the radial unit vector. Okay. For that, what are we going to do? Pull out our formula, right? So let's do that. Let's write down the formula here. Delta x I hat plus delta y j hat divided by square root of sum of the squares, delta x squared plus delta y squared. Okay? But we still need to get delta x and delta y, right? Can we do that now? Yes, we can do that now. All right, so let's do that now. Remember, delta x was defined as the difference between the test coordinate and the source coordinate for each of these two coordinates, right? X test minus y x source, and y test minus y source. Okay? All right, so you can plug that in, and so now you can see why we need these coordinates, right? So I'm going to put in here my test coordinates are -1 centimeter and +2 centimeters. That's from here. And we're going to subtract off from that 2 centimeters and 2 centimeters. That's from here. Okay? Just the difference of those coordinates. Okay, so what do we get? We're gonna get -3 centimeters, and we're gonna get -4 centimeters. Right. Okay, so, great, we've got our deltas, delta x and delta y, so let's go ahead and plug that in, right? So what will we get? Well, we're gonna get here -3 centimeters, I hat, plus -4 centimeters, j hat, divided by the sum of the squares, which is going to be -3 squared plus -4 squared. Okay, squeeze that in there, sorry. Okay, so what do we get? Well, 3 squared is 9, 4 squared is 16, 9 plus 16 is 25, square root of 25 is 5. So we should get, again, then get that r hat is equal to -3/5 I hat plus -4/5 j hat. Yep.
Shouldn't it be a positive 4? Or a 0? Not positive, it should be 0 for delta y. Is it positive
Did I
2
make a
minus
mistake
2?
here? I did make a mistake here, yes, thank you for pointing that out. So it is not +2 here, it is -2 here, right? Which makes this -2 down, let's see, that would be the source, so that's the test, so it's -2 right here. Okay, so -2 minus 2 is -4. Okay, that makes more sense, thank you. I was looking at the picture here, and I can see that it's going down 4, so it's gotta be negative. Right. Good call, all right? So it's gonna, always wanna check yourself as you're going through these here. So we're going -3 this way, -4 that way. So that gets me from the source charge to the test location. Great. In fact, another way you can test or check yourself here is that, let's do the following. So if you just get your finger out for a second. Okay, so get your finger out. Finger out. Can you point in the direction of r hat? Point in the direction of r hat, the radial unit vector. Okay, so people pointing in various different directions. Right, you want to have the vector that points from the source charge to the test location, down and to your left. Here's the source charge. Okay. Source comes right around there. It's a good thing to write on here. Source, test, right? And so if I'm going from RST, R hat points from source to test, R hat should point down and to the left. Okay? Down and to the left is a -x and -y. -x, -y. Okay? So that all seems to line up. That make sense? Okay, so again, complicated, we have a lot of calculations here, so make sure you want to check yourself one more. Okay, so we've got here now R hat vector. That's part C. All right. Any questions here so far?
I get 5 as the denominator.
How did I get 5 in the denominator? Let's see here. If I just do the side calculation, 3 squared plus 4 squared is going to be 9 plus 16. That's 25. Okay? Take square root of 25, it gives me 5. Other questions? Okay. All right. So that's part C. Part D. Part D. And here's what we want to calculate the electric field. Right? So that's going to be our K, Q, R squared, and our R hat. All right. Well, we know some of these things at least, right? So let's go and see if we can plug in. So here, I know that K is, I'm going to round it up, 9.9 times 10 to the 9 Newton meters squared per coulomb squared. If you want to be a little more precise, you can use 8.99. I need to put in the value of the charge here, right? What value do I put in for Q? Yeah.
-6 times 10 to the -9.
Great. -6 times 10 to the -9. Again, we want to convert that to coulombs, so we keep our units straight. 6 times 10 to the -9 coulombs, right? And then we're going to divide that by the distance. Now, what is the distance between the source charge and the test location? How would I figure that out? Yeah.
Make a triangle.
Okay, make a triangle. Okay, we got a triangle. We can make a triangle here. Let's do that. So I can see a triangle like this, right? And you can see here, this is 1, 2, 3, 4 centimeters on this side, and it's gonna be 1, 2, 3 centimeters on that side. So what is the length of that hypotenuse? Yeah. 5, right, the same thing. Same thing we did before. Okay, so indeed, do I put 5 then here in the denominator? Gotta be careful, what do I put instead? 0.5? 0.05, right, because it's in centimeters, right, centimeters is a hundredth of a meter. Right, so we're gonna put 0.05 meters, okay? If you wanna write that out this way, you can write it out this way, right, you can write down 0.03 meters squared plus 0.04 meters squared. Work it out, you'll get 0.05 meters, okay? Okay, but we do need to square that, so let's put the square in the denominator like this. This, okay. All right, and then we need to multiply that times our r hat. Okay. So let's do this, the prefactor here first. Over here. So what does that equal then? What does this prefactor equal? Can you just multiply that out for me? It's essentially the magnitude of that electric field. Calculator. If you have a calculator, get it out, we'll be using it today.
$21,600?
21,600, is that what you got?
Yeah, negative.
Negative, yeah, okay, negative. Anybody else get that?
I got that.
You got that? Okay, usually I have to take a couple people check just to make sure we don't have any typos. Okay, so yeah, negative 21,600, and just to be clear about this, right, so we've got 2 meters here, 2 meters here, those are gonna cancel out. We have a coulomb here, 2 coulombs in the denominator, so we'll get 1 coulomb in the denominator, and then the newtons are in the numerator, so we'll get always newtons per coulomb for electric field if we put in everything correctly. Okay, but we still need to multiply that times our radial unit vector, which is right here, okay, to get our components. So what does that equal then if I multiply that out? Multiply this through both terms. The answer here?
I got 12,960 I have and 17,280 J have.
Is that right? Okay, get that? Yeah. Anybody else get that? People, at least people? Okay, and again, that's in newtons per coulomb. Okay, yeah, so that would be our electric field. Great. Any questions here about this calculation? We do want to check ourselves, right? So let's ask the question. I've got a negative charge right here. Get your finger out. Okay. Point in the direction of the electric field at point P due to the negative charge right there. Should be pointing up and to the right, Why? Because electric field lines always point towards the negative terminals, okay? So it's gotta be along that line of connecting the two, but it's gonna be toward it, okay? So if I just sketch that in real quick, we'll get a picture that looks like this. Let's see. Let's do it for me. Okay, so then our electric field will be pointing this way, okay? Remember our R hat pointed this way, okay? So we expect our electric field to have a positive X component and a positive Y component, and that's indeed what we see here. Okay, so that gives us some confidence that we're at least in the right direction. Okay. So one thing you can put down here is direction of E is consistent with diagram. Okay. Up. Right. Okay, that's one thing you can do. Has units, so that's also good. Any questions here about this problem? We're gonna come back to party, so hang on for that. Okay, so this is an example of how you calculate electric field for a single point charge. All right, for better or for worse, the real world is more complicated than a single point charge, so we need to have some tools to deal with that. So one of the things we can do is we need to figure out what can we do if we have many multiple charges. So, and this is what we will follow, here is superposition of electric fields. So it turns out that if I have multiple different point charges, then the total net charge, net electric field at a given point is given by the vector sum. So the picture you can have in your mind, if you like, is maybe I have a charge here, Q1, charge here, Q2, charge here, Q3, and I'm over here at some point P. And I want to know, what is the electric field at point P, the net electric field? Okay? Well, to figure that out, I have to calculate the electric field due to Q1 at P, the electric field at Q2 at P, and the electric field due to Q3 at P. Then I do a vector sum. And that's it. Linear superposition of vectors. I will emphasize here, it has to be vector sum, right? So what you don't want to do is calculate the magnitude of the field here, the magnitude of the field here, and the magnitude of the field, and add the magnitudes. Wrong answer, okay? It's gotta be a vector sum. Okay, so I'll give you a short proof of this. Why is this true? Well, let's start off over here. So we know by definition that the electric field is the ratio of the force on a charge divided by the value of that charge. That's the definition of electric field. What is the net force on a charge? Well, net force on a charge is the force due to all the various charges in the problem. Right? We know this from Phys 1. Vectors add, forces add vectorial. Okay, so now I can divide the Q through, right, to the sum, that's just math, distributed property. But what now is then F sub n over Q? Well, that's the E sub n component of the electric field by definition. There you go. We see that our net field is equal to the sum of the individual fields. Questions here? So this is quite simple, but it turns out to be a very powerful tool for handling more complicated situations. All right, so before we get into some more quantitative calculations, it's always a good idea to have a good handle on what the field is, just kind of by looking at it graphing. So I'm going to do a couple of examples of this so you can get a sense of it. It's always a good way to check yourself as you're doing these problems. Okay, so here's the question again. So I have here two charges now, plus Q and minus Q. They're equal in magnitude, but opposite in sign. I want to know, what is the direction of the net electric field at the position of the dot? Okay. And the way you're going to answer here is, if you think the answer is up, you use A, left B, down C, right B. If you think it's something else, you'll vote for E. Okay? So think about this for a minute, and then we'll see where everyone's thinking here. everybody have their cards? You need a card. A few here. These, I suggest you keep in your folders, or we always have them. Somebody else need one? Okay. All right, we got one. All right, let's do a poll here. So, please vote now. What is the direction of the electric field and position of the dot? Okay. Some range of answers here, A's and B's and C's, but mostly D's. Mostly D's. Okay, so let's see if that's correct. So let me go ahead and put my pen back. So how do we analyze this problem? Well, first of all, we want to write down what we know. And that is the fact that we know that E, due to each point charge, is going to be K Q sub n over R sub n, R sub n hat. So n here is going to be 1. This Q1, Q2. All right, so that's what we know. So let's go ahead and calculate the electric field, or at least figure out the electric field for each of these individual. So here's, you get your finger out again. Point in the direction of electric field here due to just the positive charge. Great, okay, it should be going up and to the right. This one, right? How do we know that? Well, we're going to connect the dots here. And then we know that that force, the electric field acts along that direction. In this case, it's a positive charge, so we're pointing away from that positive charge. All right, so that's just due to the positive charge. What about due to the negative charge? Okay, so again, get your finger out again. What is the direction of the electric field in the direction of the due to the negative charge at the point here? Yeah, great, super. Should be pointing down to the right, okay? Again, along the line that connects the two, between the charge and the location of the test location there. And it should be, again, now pointing toward that charge because it's a negative charge. We know that it goes towards negative charges. All right, great. Well, now we have two vectors, E1 and E2. We need to add them up. So with that, we can use our sort of standard head-to-tail model. It looks something like this, right? And if we add those up, we see that the net field then is going to be in the direction to the right. Okay? So here we expect D to be the correct answer. Okay? Now, one thing I did here was I drew both the vectors the same length, right? Why did I do that? For some reasons. Yeah.
Is it their equal magnitude and size?
They're equal in magnitude and charge, that's true. What else? What else has to be true to make that true? Yeah.
The equidistant.
They have to be equidistant, right? We have to have both the Q's and the R's. In fact, I should have R squared, sorry about that. What's that? R squared here. Come on. Locked up on me. Hello? You're just locked up. There we go. Square right there. Come on. So yes, so if I have the same charge, same distance, then yes, indeed, I should have the same vectors, right? In terms of length. It would be different directions, but the same length. And if that's the case, then you'll get the direction should off to the right. If that were not the case, then the vectors would be different lengths, and you would get some other direction. Okay, any other questions here? Any questions here? Okay, so D is the answer. All right, let's try this one. Okay, again, two charges, same magnitude, different signs. And I'd like to know, what is the electric field at the position of the dot? Let's do a poll here. Please vote now. Okay, some various answers here, B's and D's and other ones, mostly B's. All right, so let's see, again, let's check that one out. So in this case, again, here we know, as before, E is going to be equal to Q, AQ, and over Rn squared times Rn hat, okay? And again, we can call this a Q1 and call this Q2. All right, so let's go through this now. What is the electric field at this dot due to the positive charge alone? Please point in that direction. Okay, I see people pointing off this way, and that is correct, right? Positive charge is going to point away, so this dot should be pointing off to the right. Okay, so here we go. E is this way, 2, 2, 1, 2, 1. What about the direction of the electric field due to the negative charge? Can you point in that direction? Right, yep, let's see them pointing off to the left, and that is correct also. So, different colors, so, yeah. So that would be out this way. All right, that'd be 2. Okay, so does that mean that the fields cancel out? I see same direction this way as this way. Looks like E. Is that, so people are shaking their heads. Why not? Why is it? What's wrong with that logic? Yeah, let's keep.
The negative Q is a little bit closer, so it would have a stronger influence.
That's right. I have to account for that, right? So here, R, the distance, is smaller. When I have a smaller denominator, I have a bigger fraction, okay? So I should have really drawn E2 to be bigger, right, than E1. It's closer. So maybe draw it like this instead, okay? In that case then, if I add those two vectors up, right, head to tail, yeah, I'm still going to have a vector off to the left. So here, we expect B to be the answer. Okay? All right. So, again, just it's a good idea to be able to kind of look at these diagrams, get a sense of where the field is, what direction it is at the very least. And then when you go through your calculations, you can check to see, does your end result match up with that intuition? Okay. All right. Great. All right. So we talk a lot about electric field, but we also like to be able to calculate electric force. So we can do this because we know two things now. We know that the force, electric force, is equal to the charge at a given point times the field at that point. We also know how to calculate the field, right? So you can see that if you put this equation into that equation, right, you get a third equation, and that's this equation here, given by the name Coulomb's law. Okay? So Coulomb's law tells you that the electric force on a test point charge capital Q due to a source point charge little q that's separated by distance r is given by this expression, 1 over 4 pi epsilon naught, okay, QQ over r squared times r. Okay. So here's our diagram now. I've got some source charge here, little q, okay, which is creating an electric field at this point, okay, where I've now put a second charge, capital Q, okay. So this is considered the source charge because it's creating the electric field at this point, and this is considered the test charge because this is where I want to measure the force, okay. So the test location of the test, in this case test charge, is going to be where I'm measuring the force. All right? So that's another way to calculate the force. So let's recap here. Oh, sorry, any questions about Coulomb's law? Let me switch slides here. So some notes about Coulomb's law. So if you have two like charges, they're going to repel. Right? We knew this already. But we can see this in the picture here. So I've got a negative charge here, negative charge here. They're going to repel off in opposite directions like that. Okay. So that's what we would expect to have happen. And we can see that from our picture, right? So in this case, let's say, suppose we want to calculate F1 on 2, right? So this is notation means the force of 1 on charge 2, okay? Well, the radial unit vector that points from my source charge to my now test charge is to the right, okay? And then the value of this charge then is, let's see, so let's go this way. So my source charge is here. Let me write this down because it'll be hard to follow otherwise. So Q1 is my source charge, okay? And this is my test charge. I want to calculate the force on this charge here, right? I'm going to have F equals K, in this case Q1, Q2 over R12 squared times R12 hat, okay? So the vector that points from 1 to 2 is off this way, right? And we now look at the product of my charges. Well, Q1 is negative, Q2 is negative. What's negative times negative? Positive, right? Negative times negative is positive. So if I take a positive number times this vector, yep, I get a vector in that direction. Okay? So similarly over here, okay, now we sort of switch places. If I want to calculate the force on charge 1, this is now my source charge. This is my test charge. Now my unit vector, radial unit vector, so this is R12 hat. Now my radial unit vector points from the source to test, it's this way, R21, okay? In that case then, I would have, this is F12, F21 is equal to K Q1 Q2 over R12 squared times R21 hat. Here again, Q1 times Q2 is positive, so my vector points to the left, as expected, okay? So the math corresponds to the depth graph. Any questions about that? Okay, and you can do a similar analysis here if I have two unlike charges, right? In this case then, here, right, if I think about it, if I want to calculate the force on Q2 due to Q1, right, my radial unit vector would point to the right from the source charge to the test location. So this is now my source, my test. Okay. Then my radial unit vector would point out this way, R12. But now, what's the product of my charges? Well, Q1 and Q2, negative times positive is a negative, right? That's going to flip the direction of the force the other way. I'm going to attract the force. Okay? And you can do the same thing for the other charge. Okay, so this is an example of how then you can use Coulomb's law to calculate forces. One thing I just want to point out here is that you'll note from the picture, and you can see from the equations as well, the forces on each charge are equal in magnitude, but opposite direction. Right? And that's true even though these two charges are different. Right? Sometimes students say, well, if say Q2 is bigger than Q1, it must be a bigger force on Q2. No. Same force on each charge in terms of magnitude. Okay. Even if the charges are unequal. Because what matters is the product of the charges, and that doesn't change. Okay. Any questions here? Okay, so again, we have two choices then when we're calculating forces. Our first choice is to first calculate the electric field at a point in space, and then use F equals QE to calculate the force. That's method one. Method two, we can directly calculate the force using Coulomb's law. Okay? The key point there is if you're going to do that, make sure you know which one is your source charge and which one is your test charge, so you make sure you get the proper direction for your radial unit vector. That's the only little tricky thing you got to be careful with. Here it's always pretty clear because the charge is the charge and the point in space is the test location. Right? Here you have to be careful. Key point is both methods will give you the same result if you do it properly. So again, I'll refer you back to the textbook. You probably read this already, but now that you've seen this, go back to section 2.5. There is an example problem where it looks at both ways, so you can see comparison. Okay, sometimes students ask, well, how do I know which method to choose? You choose whichever one's easier, right? So if I already know the electric field, right, I can calculate the force straight away because I just multiply times Q. If I don't know the electric field, well, then maybe it's quicker just to use Coulomb's law. So whatever works for you. So let's go back to our worksheet. There's a little second part to this problem. Second part of the problem says there's a second small sphere with a charge of plus 3 nanocoulombs located at -1 centimeter, -2 centimeters. Okay? So the question we want to ask now is, what is the electric force at the measured location? Okay? So see if you can figure that out. In 2 minutes here. Do that. I wanna know, what is the force on this second charge here? You don't have a calculator handy, at least write down the equation. If you have questions on where to start, please raise your hand, I'll come over and talk to you.
Oh, I'm sorry. Questions?
If you think you get an answer, check with your neighbors here, see if you get the same answer.
Okay. What are our two methods? Okay. Okay. So which one do you think you want to try out here? What do we do anything with that here? No, we charge. No, we actually pay. No charge, yeah. What else we know? What do we do with part D? Electric field. So I know the charge and electric field. Can I get the force? Okay, so see if you do. Yes, questions?
You'll get some units for the one you want. So, okay. What equation do you use? That's when you electric field going first. There are two methods. Good question, Jeff. If you already know it, you don't have to redo it. Do you already know electric field? The same test that comes down to here, yeah. That's the same source charge. That's right. We already know that. Okay, you can't have these all, but you want to keep it separate as vectors, since I had J. Always vectors, I had J. Yeah. So make sure you put the I hat here and J up there.
Charge,
Mhm.
charge you bring it off of that, so it'll be just, that name will just be.
That's right. That's right, yeah. Okay, let's see what we end up with here. Making some progress anyway. Okay. All right, so did anybody get an answer? There's two people got answers, I saw, walking around. Someone give me their answer. What'd you get?
I wasn't sure if you wanted it in like the components, so I did both, but I got
Yeah.
a 3.
Force is always a vector. Always a vector. Okay.
3.8 times 10 to the negative fifth I hat, and then 5.18 times 10 to the negative fifth for J hat.
5.8?
5.18.
Okay, sorry. What units is that?
Newtons.
Newtons, okay. All right, anybody else get that value? Raise your hand if you got that value. Got one person on, 2 people, 3 people. Okay. Anybody get a different answer? Okay, so we still have a lot of people working. Okay. So, let's see. So, let's talk about how we might do this problem. So, we've got 2 choices, right? Method one, that's where we take the electric field and we multiply it times the charge, and that gives us the force, right? That was our first method. So, to use this method, we have to know either the charge or the electric field. Actually, we need to do both those things, right? So, do we know the charge? Yes, we do. Okay. Do we know the electric field? Yes, we do. It's from part D. Okay. So, we can plug that in, and we do that. And what do you get? We're going to get 3 times 10 to the negative 9th coulombs times the value we had before, which was the 12,960 newtons per coulomb times I hat plus the 17,280 newtons per coulomb times J hat, right? Yeah. And I think you find if you multiply this through, you will end up with that answer. Okay, so that's one possibility. What's the other possibility? What's the other approach I could take? What? Different law, but on the right track. Coulomb's law, right? Those are other possibilities. Let's try that out too. So method 2, we're going to use Coulomb's law, okay? In this case then, let's just make a little plot here. So here's my charge, capital Q here, Q1 call it, and then here's my other charge down here, that was a 2, 2, and then we have a charge here, that's Q2, that's the new one, that's the 3 3 nanocoulombs. Okay, is negative 6 nanocoulombs. All right, so in that case, then we could calculate the force this way. I could calculate here, F equals K, Q1, Q2, over the distance squared times the r hat vector between those two, from source to test. That's our Coulomb's law approach. Okay? So the question is, which one is the source charge, which one is the test charge? Right, so is Q1 the source charge or the test charge? Source charge. Okay? Right, why? Because over here, so this is what's actually creating electric field over here. Okay? So this then becomes our test charge. We want to know the force here, right? If I want to know the force here, that would be a test charge. But here, this is source, test. Okay? So, in this case, it's going to be my test charge. It's going to be my source charge. Okay? So, all right. So in that case, then, I can go through this problem, and I can stick in here 9 times 10 to the 9th, Newton meter squared per Coulomb squared. I can stick in my two charges, negative 6 times 10 to the negative 9th, negative plus 3 times 10 to the negative 9th, divided by the distance squared, which is the same as we had before, 0.05 meters, that hasn't changed. And then we multiply times the r hat vector, and that r vector is the same as we had before, right? Because that's still the vector which points from this location down this way. So multiply this times the negative 3/5 I hat and minus 4/5 j hat. Okay? And you will see here, if you calculate this out, you should get the same results. Okay? So, encourage you to do that at home. Any questions here about either of these approaches? One, method two. In this problem, method one's easier, right? Because you already know the field. Just multiply times q, it's much quicker. Okay, great. All right, let's see. Why don't we go ahead and we'll take a little break here. We've been going on this about an hour. So we'll come back about 4:40, right? And then we'll continue on this. About last time also about visualization, right? So one of the things about electric fields is that you can't really see them, right? They're invisible to the human eye. So, but we do want to have some techniques to sort of visualize what's going on in some of the systems. So we're going to talk about that a little bit more here today. So we had shown these pictures last time. So we have here, in this case, on the left-hand side, again, I want to make sure these are sort of completely independent systems and not interacting with each other. So just have a single point charge. We know that we'll get vectors, of course, pointing away because it's a positive charge. And we know that those vectors should decrease with distance because we have a 1/r² dependency, right? So as you get further and further away, the vector should be getting smaller and smaller, right? Let me see that in the picture. Similarly over here, for the negative charge, right, we had negative charge here. In this case, also, we see that the length of these vectors falls off with distance, right? But of course, the big difference here is now all the vectors are pointing towards the negative charge. That's what we expect to see. Okay, so now, though, we have the ability to deal with more than one charge, right? When we started this, we only knew how to deal with one charge. So what if we were to put both of these charges together next to each other, right? What would that field look like? Right? So that's what I want to explore here next. So this arrangement of a positive charge next to an equal charge with equal magnitude but opposite in sign is called a dipole. Okay? So what I'd like to know is what is the field vector diagram going to be for a dipole? Okay? So here's what I'd like you to do. Pick a few points up above here, in the middle, and then down below here. Okay? And at each of those points, can you figure out what is the net electric field at that point? Okay. And you know, one way I usually do this is I'll think about what's the field due to one charge, draw that in. What's the field due to the other charge, draw that in, and then do a little vector sum. Okay? So, again, make a few dots, above, middle, and below, okay? And then see if you can figure out, at least approximately, what will those vectors look like. So go ahead and do that right now. use what we know about electric fields of the point charge to do this. Once you have a picture you think is reasonable, once you see, turn to your neighbors, see if they have, compare your diagram to their diagram. See if they're the same or different. If they're different, make sure you can explain why they're different or figure out what's going on. Someone next to you, behind you. That'll work.
Three dots, so I use three dots. I did that and that a little bit. Since it's positive and negative, it's getting closer to each other, then
I just put
he only said a sketch though. It's a sketch.
No, go ahead and say whatever it was, the first thing that just came to your mind. You're like, yeah, wake up.
You're better neighbors.
Did you just sound just a big, hairy American movie machine?
Yeah, that's what he said.
Okay. Everybody have a chance to share out their diagrams? All right, well, let's talk about this one then and see what you come up with. So I'm going to go ahead and draw a few dots just to have something to work with here. So I'm picking maybe a dot over here, 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 pick a few in the middle, and maybe we'll pick a few down here as well. Something like that, just to get a sampling. Okay. So let's go through and figure out what the vectors are just for the positive charge alone. I'm going to do those in red. Okay, so let's go through. I want you to go through and go ahead. Can you point in the direction of the electric field at each of these points as we go along? So what should the field be over here?
Which one?
Yeah, we can
Sorry.
see here, too.
This one here. Can you see it? This one? Upper left corner?
Oh, yeah.
This one here.
They're just a positive.
Just the positive. Okay, yeah. Should be up and to the right. Right. The way you want to think about this is you connect the line between the two. It's going away. So it should be something like, something like this.
Hey, can you figure out if it's the end of
A little persnickety today. Here we go. Like that.
Wait until all the.
Similarly over here,
Just wait.
right? And up here, like that. Okay. Okay. What about if we go down below here? You want to connect the dots, sort of like, so it should be off this way. Now, it should be bigger or smaller than the vectors up here?
Small.
Why small? Further away, right? So I'm going to make a little smaller vectors down here. A similar idea, away from the charge, but smaller than we had on the top. Okay? What about in the middle? Well, again, I'm going to connect the dots up here, and maybe we'll get something like this. This is probably a little bit bigger, just closer, bigger even still, that's probably, and then maybe over here like that. Okay? So let's just do the positive charge. What about do the negative charge? Let's go and do that. We do that in blue. Okay. Do that. All right, so here now, let's start with down here. So for the negative charge, I'm going to have field vectors that are pointing which way? Toward the negative charge, right? So for example, down here, let me point it this way. This way, okay? And then maybe like this, and maybe like this, okay? Up here, and toward the negative charge, right? So again, connect the dots between those two. So okay, these should be smaller than the ones down here. And then here, right, again, these are a little closer now, so I'm going to make a little bit bigger vectors, but again, towards the negative charge. And then this one here is even bigger still, probably, down like that. Okay, so those are the fields separately. Now, at each point, you need to do a vector sum, because I'll give you the net field at each point. So if we do that, maybe I'll do that in purple, a combination of blue and red, right? Okay, so let's go here. So if I do a vector sum here, I'm going to get something which still points up and to the right, but smaller, okay? Something like this, maybe. Likewise here, and likewise here. Okay, actually, probably not this way. And then over down here, now in this case, the bigger one is the blue one, so that should be kind of a predominantly off this direction and this direction. And then here again, I'll have predominantly this direction. And then finally here, if I do a vector sum, I'm going to get a vector that points down this way. Vector sum points down this way. And of course, this one will go down like that. Okay, so the purple vectors here are the net field vectors. That's going to be your field vector diagram for the dipole. Okay? All right, so how'd you do? So? Okay? Right. So here's a nicer picture, right? This is a computer-drawn picture. But same idea, right? So interesting about the dipole is that it kind of looks like a positive charge above, kind of looks like a negative charge below, but then in between, these vectors just point straight down, which is different than what we have for a single charge. Okay, so again, I expect you to be able to draw some simple field vector diagrams, right? Pick a bunch of points in space, figure out what the vectors are at these points in space. Questions? Just some other examples, just to give some sense of it. There's another way, too, to be able to draw, to do visualizations for fields, and that's called a field line diagram. So there's some rules about how you do field line diagrams. So let me talk about that. So the biggest difference between field lines and field vectors is that the lines are sort of continuous in nature. They kind of go, there's no starting or ending point other than charges. We'll talk about that in a moment. And the key point here is that at every point along that field line, that's the kind of the pink curve here, the field vector has to be tangent. Right? So you can see here, this vector is tangent, this vector is tangent, this vector is tangent. Right? Every point along the way, I could pick a point and I could draw the tangent. That would be the direction of the field vector. Now, if I took those field vectors away, which is what you would normally do in a field line diagram, then you wouldn't have any idea how strong the field was, right? Because it was the vector length that told us the strength of the field. So the convention then is to draw the field lines closer together where the field is stronger. So here you see the vectors are longer, and so the field lines are closer together. Here the field lines are smaller, field vectors are smaller, so the field lines are further apart. That's the convention. So those are the first two rules. Third rule, electric field lines can never cross. Why is that? What would be the problem if I had two field lines that were crossing? Yeah.
Because the field can't point in two directions at once.
How do I draw a tangent at that point? Can't, right? It's undefined. So field lines can never cross. And lastly, field lines can start and end, but they can only start on positive charges and end on negative charges. Okay? Otherwise, they're sort of continuous through space. All right, any questions about these four rules? So let me show you some examples. So here's the field line diagram corresponding to the field, to the dipole that we just talked about. Okay? What do you notice about this? What's different? What's different, what's the same? Throw some things in. Yeah, okay.
It still looks mostly like a positive charge on top, a negative charge on bottom.
Fair enough. That's right. Okay. That's a similarity. Any differences you notice? Yeah.
So the line's got some curves to them.
Got some curves to them, right? Before we just said straight, vector's always straight, right? They act at a point, and they're always straight. Here we kind of a little more curvy, right? So maybe some people like it, so maybe it's more aesthetically pleasing. They like, maybe fills out the space. It's a different way to think of things. Where is the field the strongest?
In between the positive and negative charge.
Right in between the two positive negatives. How do you know that? How do you know that? Field lines are closer together. They're denser here. Okay? Again, that corresponds to what we saw before, right? Where was the field lines biggest? Field vector biggest? It was here, right? So that makes sense. Okay? Makes sense. Okay, so again, here they've drawn a few field vectors on. Normally you would not see those field vectors on. Okay? Just to give you some sense of it. So again, here I expect you to be able to kind of draw and interpret both kinds of vectors. Let me show you another example just to get familiar. This is a field line diagram with a few field vectors superimposed for two charges, again, but now both the same sign, equal magnitude, but and both positive. Okay. So, anything you notice here? Serious repelling going on. Okay. What about the middle? Is there something wrong here in the diagram? Why are there no field lines there? Dead zone? Why is it?
Try to push it out, try to escape. You don't want to get bound up in the middle there.
Okay. Yeah.
The forces are canceling each other out at that center point.
Yeah, the fields are canceling out. Yeah, so let's think about that. If I pick a point right in the middle here, okay, and I were to draw the vectors associated with these 2 points, what would I get? Well, I'm going to get a vector pointing downwards from the top charge, and I'm going to get a vector pointing upwards from the bottom charge. Right? Those are going to be equal and opposite at 0. I'm going to cancel out. Okay? And when I have no field, I have no field lines, right? Because in the extreme case where, if we say the density matters, right? If it's stronger, it's going to be denser. If it's going to be 0, it's going to be nothing. Okay. So here, that's not a typo. There's no field at that exact point right in the middle. Okay. So another example of a field line diagram with a few field vectors. A few more examples just to give you some sense of this. Right? So what if I had an infinite line charge? Okay, so I have a bunch of positive charges all along this, up to positive infinity, down to negative infinity. What would the field look like? Turns out you can show, we haven't talked about this yet, but you can show the field will point away, of course, from the positive charges, but it will fall off with distance. Turns out it's 1 over r dependency, r being the distance away from the line. And so you can see that here. The field vectors are getting shorter as you go on. It's a field vector diagram. Another example, an infinite plane. What if I had a charge kind of smeared out over an entire plane? What kind of field would I get? What is this? What kind of field do I have here? How would you characterize that?
I literally got an email.
What do you notice about the vectors here? All the same. Okay, they're all the same. Does it matter how far away I am? No. Same at every distance. Okay? So for a truly infinite plane, electric field is uniform at every distance. Interesting. Okay? We'll talk about that a little later. If I take a positive plate and a negative plate, put them next to each other, right? I get this field. It's a field line diagram. What do you notice here? Straight lines? Okay. What else?
It's the same. all the way down.
Same all the way up and down, right? So you notice the spacing here is the same, right? It means it's a uniform field. Okay? So if I want to make a nice uniform field, I can take two plates, put them together, and I get a uniform field. Does anybody know what this device is called? We'll come back to this later. So, anyway, some examples of field vector diagrams and field line diagrams. Any questions here? Okay, just make sure you get a little familiar with these. All right, let's ask you, I'm gonna ask you a question, see if you, how well you understand. Okay, so here we go. I've got now, let's suppose I have these four boxes, each one of which is a field line diagram, okay? And consider these to be four completely independent scenarios, so they're not interacting with each other. The question that I want to ask is, which of these patterns represents a possible electrostatic field? In other words, something I could physically, realistically construct in space. The other thing to note here is that it's assumed that there's no charges in any of the boxes. All the boxes have no charge in them. Right? So, again, assuming that there's no charges in the region shown, which of these patterns represent a possible, physically realizable electrostatic field? Okay, let's do an initial poll here, see what you're thinking. Mr. Alfred. Please vote now. Vote now. Okay, you got answers all over the place. We got A's, C's, E's, D's. All right, let's have a discussion here. Turn to your neighbor and convince him that you're right. Tell him what your answer is, convince him that you're right.
I see like I will. C looks very glossy. I don't know. I just feel like I don't like C from the fact that you see how the line just appears out of nowhere, right? And we're getting told that there's no charges being appeared. How is that possible without having a charge? That's why I picked B, because B is one solid line, so it could be possible that there's something that's creating that type of wave, as well as D. D is similar to what we saw in the beginning with the positive and negative sign. That's why I picked D and B. It's all one solid B.
Hey, you have a better argument than I do, so it's gotta be yours.
I'm telling you right now, I don't think it's possible if there can't be points in the box, it has to start with positive and then it has to. You see what I'm saying? So you're, no, let him argue, let him argue.
If there's charges, it would be kind of like a big groups where they're touching each other.
Well, about maybe 10 seconds, we'll come back together.
Oh, shit, we might not have it. Otherwise, it's hard to make it. Ignorance is bliss. Maybe you're right then. I'd just be curious where the charge would be.
Let's do a follow-up poll, see how convincing you all were to each other. Please vote now. What is the possible electric static fields in this example? All right, still seeing quite a bit of disagreement, although it seems to be converging consensus around B. Right? A few other answers, B's and E's. Okay. All right. So let's go through these one by one. So A, nobody voted for A. So what's the problem with A?
Where do we start?
Where do we start? Give me some. Let me do this one thing.
Yeah, how does that work?
Okay. So yeah, it looks like it's sort of can't figure out what it wants to do. There's looks like negative on this side. Looks like positive on this side. Okay. What's the other problem in here? What cannot exist within the box?
And then we somehow got, we got two.
Charge. Right, there's no charge in the box. So we can't have any place where the charge lines actually originate.
Maybe it's
Can't
random.
happen. Okay, so I agree, A is not a good choice, all right? So, all right, what about B? Is that physically realizable?
Yeah.
How would you do that? How would I make a field like this? What do you think?
Zoom into the middle.
Give me an example of what I'd have to do. to
Put a
construct this.
positive on the left side and you put a
Positive over here.
negative on the right side.
Negative over here. Okay. Yeah, we might have a few other charges, but yeah, that's the idea.
Might be something else to make it to this.
So yeah, I think that's reasonable. I would go for B. I could believe that.
Yeah, I'm behind that.
Okay, what about C? C.
Rough.
Any problems?
Not rocking with that.
Yeah.
We're just, I mean, we got lines starting in the middle of nowhere here.
Lines start in the middle of this.
Just.
Okay. And again, no charge in the box, but we can't have lines starting from nothing. Okay. Because there's no charges. Yeah. So again, C is out. What about D?
It's up for debate.
How many people think D? Possible. How many people think not possible? Okay, so we got it flipped about 50-50. So based on what we know now, okay, I'm gonna say no. Okay? I'm gonna say no. But we will come back to this question, hopefully, by the end of the term, and we'll see if whether or not we can actually.
We don't have to come back to it.
So,
We're good.
cliffhanger.
We might have started.
So
an
for
argument
now, we'll
over
say no
how
for
we
D.
should be finishing.
I think D here's the best answer. Okay? Based on what we know, we don't know how to construct something.
You were led astray.
Okay, any questions about this example? Any questions? I just want to make you think a little bit about field line diagrams and charges. Okay. All right, I just want to point out a few things. There's some nice simulation out there. I highly recommend the site, fet.colorado.edu. Anybody ever been to that website? People? Okay, great. This is a nice, this is one of the many apps they have there. This is called Charges in Fields. If you do a search on Charges in Fields, it'll come up. And the nice thing about this is you can drag and drop these charges from the little box down here into your space, and then it will automatically draw out the electric field. You can put a little sensor in, feel what the field is, so on and so forth. So just as an example, here's our dipole. Right, I did this at home. And here's drop the positive charge here, drop the negative charge here. And you can see, yes indeed, we do get this sort of dipole-like field. And this is nice. You can try to play around with different kinds of charges and see what you get. Okay, it's interactive. So I highly recommend this site. Okay, next up, I want to talk then about our overall strategy for dealing with now problems with multiple point charges. Okay, so again, a 4-step process here. We start with our planning step. Typically, at this point, the only thing we really know how to calculate is point charges. So we're going to model our charges as point charges, as long as that's reasonable. Right? A long line, not reasonable. But if it's a small, small enough object, far enough away, probably okay to model it as a point charge. Sketching, again, you want to put in a coordinate system, show your charges. You want to identify the point where you're going to calculate the field. You want to calculate the field at each charge at point P. In some cases, you can use symmetry to figure out, to simplify your calculations. Then, of course, in the calculate step, here's our key point. Right? When you use our vector superposition to do the calculation, you want to figure out your charges, the distances, figure the field strength, write each vector, and then sum them all. Right? Lastly, of course, then, check your results, make sure you have the correct units, correct reasonable number of significant figures. So let's look at an example. Okay, so here's the example. So in this example, we've got, in this case, 3 point charges, negative, positive, positive, different values. And I'd like to know what is the electric field, the net electric field at point A. Okay, point A is at the origin. Okay? So, that's what, and then the second part of this problem is, if I were to drop an electron at point A, what would be the force on that electron? Okay? So let's start part A first. Okay. Next slide. All right, so let's start at the beginning. What might be reasonable to put down in the model step? Do we have any simplifying assumptions here we want to write down? Key equations we want to use? What do you suggest? I need some equations at least, right? What equation should I use? Yeah.
Coulomb's law?
Coulomb's law we could use, but we want electric field, right? And Coulomb's law tells me electric force. So, is there another equation that's kind of like that? Yeah.
Should we do like a charge segment?
Charge segment? I think a charge segment is like an actual line of charge. We don't really have that here. So, Yeah.
This is the one where we get the electric fields and add them together.
Yeah, so we're gonna add them together, so that's gonna be part of this, right? What equation, but we need to find something to add together first. How do I calculate from the things we're gonna add together first? What's the equation I need? Electric field equation. What is that equation?
K,
K.
K, Q.
K times Q over R squared times R hat.
All right, very good. Yes, all right. So these things, again, you wanna get familiar with these equations, right? So, let's write that down. So we're gonna use, this equation, right? And again, what do I need to have to be able to use this equation? This equation is applicable to what kind of charge? Point charge, right? So now, the problem doesn't say point charge, so we need to make that as a simplifying assumption, right? So, let's see, let's model all the charges, let's go model that one. Model all the charges as point charges, right? If we model them as point charges, then we can go ahead and use this formula. Okay? Good to go. All right, that's our model step. Visualization step. What should I add here? We already have the charges, of course. What should I add to the diagram? That's another thing we usually want to have in our diagrams.
Coordinate system.
Coordinate system, always very helpful, okay? So in this case, we know A is the origin, so we're gonna put the origin right there. Okay, so I'm gonna draw an x-axis, sorry, y-axis and an x-axis like this. So here I'm gonna draw my x-axis, and I'm gonna draw my y-axis like this, okay? All right, great. All right, we'll keep that for now. I think the other thing I'd like to put in here, though, is I'd really like to put some labels, especially when you have multiple charges. It makes sense to have labels. So I'm going to call this one Q1, and I'll call this one Q2, I'll call this one Q3. You can label them differently. That's what I'm going to do. Okay, so let's at least start with that, okay? All right, so next up, let's go to the solving or calculating step. So let's start here. So here, let's start with calculate E1. Right? Let's calculate electric field due to charge 1 at this point. Point A. Okay, so let's write that down. I know that that's going to be then K Q1 over R1 squared times R1 hat. Okay? To calculate that, I need to know all the various things. I know Q1. Do I know R1? R1 is the distance between the two.
Yeah,
Yes, we do. Okay, that's going to be 2 centimeters. And then, do we know R1 hat?
Find it.
We can find it. We can find it. It's not given in the problem, so let's find it. Okay, so to do that, then I need to calculate, first of all, my deltas. Okay, so here now, I want the charge, the electric field at point A. That's my test location. Test location, okay? And for this particular part of the problem, this is going to be my source charge. Okay? So here I go. X test minus X source. Y test minus Y source. We can identify this. This is 0, 0. This is negative 2, 0. Right? In centimeters. So we can calculate those now. We have the 2 coordinates. We're good to go. So here then my test coordinates are 0, 0. We'll subtract off my source coordinates, which is negative 2, 0. What do I get? I'm going to get negative 2 is plus 2 centimeters, and 0 centimeters. Okay? So that means my R1 hat should be plus 2 I hat plus 0 j hat divided by the sum of the squares here, 2 centimeters squared plus 0 centimeters squared. Should have put a centimeters in here. All right. So if I simplify that out, what do I get?
One I.
One I hat, just I hat, okay? So, first of all, let's check, does that make sense? I want a unit vector that points from my source charge to my test location. I think so, right? Here's my source charge, here's my test location. Yep, I hat points in that direction. And in fact, here, you might not even need to do the calculation, right? You can almost see that. But it's good to check. Okay, so we've got that. All right, so we've got now everything we need, right? So let's go ahead and put in some values. So E1 here is going to be 9 times 10 to the 9th, Newton meters squared per coulomb squared. We're going to multiply that times Q1, which is 10 times 10 to the negative 9 coulombs. We're going to divide by the distance. What's the distance here?
0.02 meters.
0.02 meters, right? That's 2 centimeters. And then we're going to put in our I hat right there. Okay? That's my R hat vector. Okay, so at this point, get your calculators out. What do we get there? Did you get an answer?
$225,000.
225,000, we have 225, anybody else, 225,000? Yeah, anybody else get a different answer? All right, we'll go with 225,000. Okay, so that's plus 225,000, and that's in newtons per coulomb, again, times I hat. Okay? All right, so that's the contribution due to charge one. All right, I'm gonna have you do for charge two, okay? So I wanna know what is the electric field component, electric field contribution at point A due to charge 2 of them. So I'll give you a few minutes here, see if you can work it out. Questions, get stuck, let me know. Help. that's just pretty smart. So I would just start with some of these just start with four. So we have an equation. So the equation. And then use that for Q2. So use the equation to start with. And use it. And you figure out what is Q2. What is R2. And what is R2. Just break it down.
Also,
Yeah, question.
just to make sure real quick, is it better to just maximize the denominator, just like that? Or did I not do something right?
So this is for,
So we have the, oh wait, I forgot the square, that's why, okay. There we go.
how we do? Do we have, do we get an answer here at this point? Someone to share? And feel free to compare with your neighbors here. Yeah.
I got negative 450,000 newtons per coulomb J hat.
Okay, so let me write that down. So, the proposal is negative 450,000 J hat. Anybody else? Get that value? Few people? Okay, all right, few people, all right, so I'm seeing some hands up. Okay, let's see if we can work that through, make sure everybody's on board. So again, K, Q2, R2 squared, R2 hat, right, those are the key things we need to figure out. So in this case then, we know K, 9 times 10 to the 9 newton meters squared per coulomb squared. We know Q2, 5, okay, make sure you put that in coulombs, and 9 times 10 negative 9 coulombs. We're going to divide that by the distance. What's the distance here?
Here's 0.01.
0.0, it's 1 centimeter, right? 1 centimeter from here to here. Okay, it's a rectangle. It's the same over here. So that's 0.01 meters. Okay, and then, okay, we need to figure out our R2 hat. Okay, so for that, we need to calculate our delta x and delta y. X test minus x source, y test minus y source. Test location is the same, that has not changed, right? So we'll put 0 and 0 here. Our source location though has, this is our new source location for this charge. So what are the coordinates up here? What are the coordinates of Q2? Yeah.
Yeah, 0 and 1.
0 and 1, yeah, thanks. Yeah, 0 and 1, super. Okay, 0, 1. Okay, so we can stick those in here, 0 and 1. Okay? And so we subtract, we get 0, and we get negative 1. That's in centimeters. Okay, so to plug in then, R2 hat is going to be equal to, we're going to get 0 times 0 centimeters times I hat plus negative 1 centimeters times J hat divided by square root of 0 centimeters squared, negative 1 centimeter squared. Okay, and well, the denominator is just 1, so we'll end up with just basically negative J hat. Negative J hat. Okay? Does that make sense? Everybody get your finger out. I want you to point in the direction of R2 hat. It's the direction from the source charge to the test location. Where's your source charge? Down, right? That's the direction from the source charge to the test location. What direction is that? Negative J hat. It's a negative Y direction. Okay, so it does make sense. Okay, here's one of these situations. You may not even have to calculate it if you can see it from the diagram. Okay, so that does make sense. So we're going to stick it in here, negative J hat. Okay? All right, so calculate this out. I think you will find that in fact it is negative 450,000 J hat units per couple. That's what I got. How'd you do? Okay? Some people got it? Okay, great, excellent. All right. All right, last one then. Q3, you know what to do. Questions, let me know. Brothers.
So that, so when we plug in the we'll just make that side.
Well, because the thing is, it's 0.05 squared.
But it's a square root. Square.
Oh, sorry, yeah, you're right, sorry, I didn't realize we had those squared, so. I think that's, so it's gonna be square, let's be sure, 0, 2, 2, 2, 3, squared. So it's gonna be, this is the distance here, this is actually the square root of 5, right? So, but it's in centimeters, we put in centimeters, and then, sorry, it's in centimeters, convert to meters, and then squared. So just be careful about that. Yep.
Is it going from that point, so
It's out of time here. So it's a little different. So what's the coordinates of Q3? Yeah, it's gonna be negative, right? It's because the same distance over, but then it comes off. So it's something like. Well, also 2, and then measure it also. So here in the numbers, the square root of this part here, it's square root of 5, and the whole thing. So it's going to be 2 to the square root of 5 for the first term, negative 1 to the square root of 5 for the second term. Okay. I want to do that. All right, let's come back together here. Thank folks for making good progress. Okay, so here we want to go ahead and do the same kind of thing. We want K, but now Q3 over R3 squared and R3 hat. Okay? That's going to be 9 times 10 to the 9th, Newton meter squared per coulomb squared, times my charge, which is negative 10 times 10 to the negative 9 coulombs, divided by the distance. This is something we have to calculate, right? But we can do that. How do I do that? I want to know the distance R3 here.
You convert it to centimeters, then square it, and then unsquare it.
Okay. What theorem are we going to use?
Right triangle theorem.
Okay, our Pythagorean theorem, right? So you're on the right track. I know what you're talking about. So yeah, so here basically it's going to be the square root of this side length here, right, which is 2 centimeters.
What's important is that I know what to do.
plus 1 centimeter, right? That's what you were trying to say, right? Okay, so that's gonna give me square root of 5 centimeters. That comes out to be about 2.23, I think, something like that, more or less. Okay, so that, we're gonna convert that to meters. Should get something like 0.0223 or so meters squared, right? And then we're gonna stick that in and multiply that times R3 hat, which we need to calculate. Okay? All right, so R3 hat, let's do that. R3 hat is going, let's first of all, let's calculate our deltas. Okay? So deltas here, delta x, delta y. This is our source charge for this part of the problem. So we're going to have here x test minus x source, y test minus y source. We're going to get 0 and 0, right? That's still the same. Minus, coordinates up here, -2 plus 1. Right? -2 plus 1. So -2 and plus 1. So we should get +2 and -1 in centimeters. Okay? Which means that R3 hat is going to be equal to 2 centimeters times I hat plus -1 centimeters times j hat divided by sum of the squares here. Or square root of the sum of the squares. So it's going to be 2 centimeters squared plus 1 centimeter squared, -1 centimeter squared. That's going to be square root of 5, right? So, end of the day, 2 over square root of 5 I hat minus 1 over square root of 5 j hat. Okay, and that is going to go in here. Okay. Questions here? Let's see. I got, I'm gonna have to squeeze this in over here. I got E3 was equal to 161,000. Erase. Here we go. Let's start again. E3 is equal to 161,000 I hat. Sorry, negative 161,000. And then plus, I got 80,500 or so for j hat. All right, sorry, it was real messy. Oh, sorry, it's for some reason it's not showing up. Okay, I'll write it up here. E3 is equal to negative 161,000 I hat plus 80,500 j hat. And that's a new equivalent. I'm not sure why it's not showing up. Okay, did anybody else get that? Okay, few people, great. Right. So, what's the last step here? The last step here is we need to add these up. Okay, we've got our contribution to the first charge, second charge, and third charge. You know the net contribution is going to be the sum of those. Okay, so let's go add those up. Okay, so I'm just going to do that on the next slide here. Okay, so we had here then E1 was equal to 225,000 times I hat. E2 was equal to negative 450,000 times, let's see, Newton's recall, times j hat. And then E3 was equal to what we just wrote down, negative 161,000 I hat plus 80,500 j hat. Once again, Newton's equivalent. We add those up. Okay? And you notice I kind of wrote them offset because these are all the I hat components. Right? Those are your X components. These are all your J components, right? They have to be added separately. Okay. So let's see. When I did that, I got the following. I got E net to be 64,000 I hat. And I got negative 369,000 or so J. That's in Newton's per coulomb. Okay? So that would indicate that my field then is pointing up, I'm sorry, to the right and down. So something like this. That's my E net. Okay? Does that seem reasonable?
I want that.
If we look back over here, right, if we look back over here, we had three vectors, right? Three vectors, one of which was pointing backwards, pulling back like this, right? And one which is to the right, one which is down, right? So if you do a vector sum, I think it's plausible that is the correct answer here. Okay? But check it at home. Questions here? Okay. I'll stick around a little bit afterwards if you have individual questions about asking. Otherwise, we'll call it a day, and then we'll see you here on Monday.